Welcome to our first episode of Distributive Deep Dive. In this series of videos, we're going to be talking to interesting people who have worked on distributed systems. In our first series, we're talking about hidden scaling issues and distributed systems in the real world. And today we have Paul and Paddy, and they will be talking about the real problems they face when scaling internet scale systems. And we're hoping that what you might learn from this is avoid some of the mistakes that Paddy and Paul have made whilst building these systems. Paul, would you like to introduce yourself?
Sure. My name is Paul Nordstrom, and I've been writing software since high school. I programmed my way through college, and then a brief detour into finance, but I ended up building financial systems. And then when internet came along, Amazon offered me a job in 1999. And I was lucky enough to come at a time when they needed somebody to do a clean sheet architecture for their website. So that was my first internet scale system, and some of the services oriented architectural things that we invented there in fact have permeated the industry. So that was a very successful system. They're still running parts of it. Some of it's been replaced. After about 8 years at Amazon, I took a break. I wanted to change a venue. I went to this other little internet search company called Google. And at Google, I was in charge of the design and building of a system that's been published. So if you're curious about some of the examples, you can read the paper called Mill Wheel. And I was at Google for about 10 years.
Excellent. Paddy, would you like to introduce yourself?
Sure. So my background is a mathematician. In my doctorate, I worked on mathematical problems underpinning formal verification. In my career, I've worked on a wide range of different systems, safety critical systems, security critical, embedded, real-time, and a lot of consumer electronics. At Ably, I've built the core real-time messaging product. And although we have a growing engineering team now at Ably, I still spend most of my time coding, building the next set of features for the product.
Paul, so if it's okay, we'll start with you. The first question I think we'd like to talk about is we have a good understanding of what the textbook problems are with scaling distributed systems, but I think in the real world, the problems we encounter are the problems we didn't expect. Can you tell us a bit about your experience with this?
Sure. The first thing you do when you're designing a system, you try to figure out which dimensions it's going to scale in, right? And that's the part you were talking about that we usually understand, although doing a good job of that involves shedding some of your ego, involves involving other people in the design discussion, because there are things you're going to miss. And you obviously want to minimize the things that you didn't think about in advance. So that's the first step of dealing with the unintended scaling issues, is to not have some of them. Once you get past that, though, you have to accept the fact that you're going to run into problems that you didn't anticipate. And even if you've done a great job of minimizing it, the real world just throws more. The world of software is more complicated than a human mind can encompass. So you do everything you can. You build mathematical models for your system so that you have a coherent framework within which your system is going to operate, and you can reason about it using the mathematical model. So that's a great first step. And I think that in the industry, that's one of the things that gets short shrift. I think few people really do a good job. And it's one of the things I found when I started looking at Ably I was most impressed with, was that it had a mathematical model, and you could understand what it was intended to solve, what problems, what scaling dimensions it was supposed to. Okay, so Millwheel was the same. Millwheel has a mathematical model for distributing computations on time series. It treated a time series as a foundational abstract thing that you could reason about. Okay, but to get on to the meat of your question is, once you've done everything you can and you find that you have unintended scaling problems, well, what do they look like? And maybe having heard about a couple of them here, you can help anticipate that happening to your systems. one unintended one that you think of in advance and convert it into a known problem in advance will make an incredible difference in the quality of the system you build and the time within which you get it done, because solving these problems after the design phase is, sort of order 10 to 100 times as difficult, right? We all experience that. Fixing a bug takes at least 10 times longer than it does, solving that bug in advance by making a good design. So, in Millwheel, one of the things we didn't anticipate was the rate at which, so Millwheel has this partition space, okay? Every piece of data being manipulated has a key. And so let's say the key is, let's say the data that you're manipulating is Google queries. In fact, Millwheel actually is used to process the stream of Google queries received on the internet. And we anticipated that, some queries happen more often than others, okay? We didn't do a very good job of analyzing the data, and we didn't realize there was this one query that is so far exceeds every other query that not a single machine could handle the processing of it. It happens to be the query Google. People type Google into the Google search box with great regularity, more than any other single query, okay? So if we had talked to the team, one of the reasons we didn't anticipate this is we didn't know that Millwheel was going to be applied to this problem. We couldn't talk to the team that did it. But we could have done a better job of talking to more of the community about what they might use a system, because it was fairly well understood that Google needed a system for processing continuous data at the time. They had MapReduce, and MapReduce is a big, enormously scalable batch system that solves a great deal of problems, but not the continuous data problem. So all of these are they're little lessons, but they add up. Spend more time talking to your users about how they would use your system. Show your design to more people, and just shed the ego and shed this need for secrecy if you can, so that you get a wider spectrum of people who can tell you, I'm going to use it like this. And then when you run into the inevitable problem, then you just have to that having done the work that you did before, your system will be more cleaner designed. You'll have this mathematical model. Then at least when you get into this case of a problem that you didn't anticipate, you'll have a cleaner bed from which to solve it.
Okay. Do you want to add anything to that or not?
Yeah, I think just to echo what Paul said. So when you set out to build a system, roughly speaking, what the first order problem is you're trying to solve. The scaling problems you run into are the second order problems often. So it's not just how many messages can I support in the channel, but second order problems, rate of change of number of channels or rate of change of number of messages. Sometimes you're caught out because the engineering catches you out. Things turn out to be harder than you thought. And sometimes the user catches you out. So they use the system in ways that you didn't expect when you designed it. So you find a whole bunch of new use cases that you then have to go and deal with, or they give you scaling issues that you didn't solve originally.
Okay, so let me add to that sometimes you're going to come across in your attempt to solve a problem one that can't be reasonably solved. And sometimes you just have to accept that your system can't scale in every dimension. And you might just have to say to the customer, inherent in our system is a limit on the number of channels we can support, or the rate at which you can add new channels, or whatever it is in your system. In fact, tying this back to the Millwheel problem, one of the things we said is if your key space can't be partitioned so a single key can be handled by a single machine, we're not going to solve that for you. You're just going to have to find a different solution for that problem. Okay? And I think it's important to realize that trying to make your system solve every problem eventually ends up with either a system that's too complicated to use or one that doesn't work very well for any of the problems you're trying to solve.
The limitations of the system and the things that are the limits of your scaling parameters is obviously important from the start. How do you think you go about understanding those limits? Do you understand them once you built the system, or do you think you can preempt some of that, or do you think you just deal with problems as they arise in areas that you may not understand fully?
Well, I think the first point is that you have to understand at least one scaling issue from the get-go, which is the scaling issue that your customers have that you're here to solve. right? If you haven't talked to people about what their needs are, and you haven't clearly identified the way in which your system is going to scale in dimensions they need, you haven't done your homework, and you're doomed to failure, unless, without just great luck. So if you have chosen a set of scaling dimensions that you're going to attack with your design, right? Then you study those dimensions and you make sure that your architecture, I think that people get this part though. I think that they understand that you need to solve the issues of their customers. I think they understand how to design. It's the second order ones you get. And we talked earlier about how to at least try to head off some of the issues with the second order scaling issues. But really the answer to your question is, if you've done your homework and you have addressed the issues that your customers need you to solve, and hopefully you're providing something nobody else does, or that you are much better at than other systems out there. Your systems need to have a competitive advantage too. So they need to solve customer systems or customer problems better than the other systems that are available to your customers. Then you're going to have a successful system. Whether or not you end up with second order scaling issues that you can or cannot solve, you've met this primary need. And but what I think is very important is that you're really clear about, clear thinking and have a clear process for identifying those and solving those.
Paddy, do you think, when designing, building, and then running ably at scale, do you think there's been second order type problems that even now, looking back, you think it would have been hard to predict what those problems were until those problems arised? Are there any sort of specific examples you can think of that kind of, show how difficult it maybe is to predict these types of problems sometimes?
Yeah, I think the kind of example that comes to mind is the sort of thing I mentioned where the customer catches you out. So they're doing something you didn't anticipate. So we built something imagining that channels were long-lived, and we optimize to the greatest extent possible the cost of processing a single message. But that catches you out if what the customer's really doing is they're creating and destroying channels at a very high rate. Another example is fan out. We imagined we'd be dealing with, typically one of the scaling dimensions is I want to be able to fan out messages to a very, very large number of subscribers, but then we have customers who don't have that problem. Instead, they have channels with a single subscriber, and what you need to do instead is minimize the cost of establishing the first subscriber, not establishing the millionth subscriber. The other thing I would add to that is, in understanding the scaling limits, I think what you have to look out for is what's an order n feature of your system, and what is or can be a better than order n feature of your system. So if everything in the end will become a limit to scaling, the question is, do I have to deal with it now, or do I know I can deal with it up front? So if it's an order n thing, I know I'm going to have to deal with it at some point, but do I know a way that I could improve that when the time came, or is it something I have to address now?
Yeah, I think that's one of my fundamental precepts of the building of a system. Even if you have a pretty clean idea of the design, you can't build every dimension of your system to its ultimate capability on the first pass. You have to pick ones that you can, that you understand well enough to build right. You should build those right. But the ones you don't understand well enough to build right, you should build a hack that has a shell around it that you can then use as, let's say, an interface or a abstraction layer, but eventually, but not actually try to build it when you don't know enough to do it. And one of those things is when it's a customer, this is tying off what you just said, when what you don't really know is how people are going to use it. And then, it's not that you couldn't solve one of the problems that you don't understand, but it's you don't know which is really your problem yet. And then you have to make you can make a much better decision later on.
How does what we've been talking about relate to microservices?
Well, you're pushing one of my buttons here, because personally, I don't think there's such a thing as microservices, and I consider the whole thing to be a giant buzzword that people have used so they get internet audiences and so on. I think that services span a range from very, very small, which you're free to call those microservices if you like, but there's no cutoff where they start becoming not microservices. They just get bigger and bigger until they're gigantic services that have large-scale functionality. And your choice of the use of these depends on your problem, and you should choose the right one for the job. And you should make a balanced choice between functionality, complexity, power, size, etc., and ease of use. And so, if it were up to me, I would wipe the term off the internet discussion lists and get rid of it. But the important thing about the microservices movement, in my opinion, that was valuable is that the tendency should be to push yourself down the scale when possible, when appropriate. The smaller service is probably the better one. It's easier to reason about. Okay, it's easier to swap something else in if you need different characteristics than the choice you made at the beginning of the problem. So I don't believe in microservices. In fact, I probably will never say the word again after this interview. But I do believe that learning to balance the use of out-of-the-box components and to choose wisely should be geared towards, aimed towards the smaller of the two choices if all other things are being equal. I think that's important. Okay, but that said, often microservices are in contradiction of the need of a system to scale in dimension, because one of the ways you get scaling out of a particular functionality is to couple two parts of it. The tightly coupled one usually outperforms the loosely coupled one. Okay, and architecture composed purely of microservices, in the long run, if it's attacking a truly difficult scaling problem, I don't think you're going to, in general, be able to solve it just by composing microservices, no matter how well you do. I think you're going to be forced to choose, in certain cases, to couple the search semantics with the storage semantics, for instance, and you end up with something like a relational database instead of something like Spanner. It depends on the situation. I'm not calling out Spanner in a negative way. Spanner was a brilliant piece of work, and it solves a huge swath of the problem space, in the dimension that it's approaching in storage, that had never been attacked before.
So Paddy, I mean, at Ably, I know we've had the discussion about the dreaded word microservices, but really I think my understanding was that the problem with splitting a lot of the services that we run up was that actually we're creating not just potential performance bottlenecks, which are probably less of a concern, but more operational bottlenecks, and that trying to sort of manage versioning across APIs, across lots of different services, just creates a lot of complexity in the system, unnecessarily so. What are your thoughts on what we're doing within the RPC layers and how components talk to each other, but still sort of keeping them as single, larger components?
Yeah, so we've a lot of what we have done, the system has grown up relatively monolithic, and we've faced the question of when is it a good idea to split something into a separate service. And as you say, there are sort of operational complexities and performance complexities that come about when you do that. However, every single thing you do eventually becomes a problem, no matter how insignificant or negligible performance-wise it seems to be initially. Eventually it will become a problem. So the real question for us is, at what point does something become significant in a way that means you want to scale it independently? So do you want to be independently elastic with a particular service, or is there a particular advantage operationally to be able to deploy it and give it a different deployment lifecycle from other services? And that's the point at which you would then consider splitting something out into a microservice. And that's broadly the approach we've taken.
I think that I wanted to add to that is that I think that you should know and be conscious of the core functionality that we talked about earlier. What problem is your system solving for its customers, and in what dimension of scaling in particular it's solving a problem for your customers. And when something's not central, it's much easier to split it out and make it something independent. And if it is central, it's much less likely to become a service by itself. Because as like I said before, the loosely coupled hardly ever outperforms the tightly coupled. You can't afford to have everything be tightly coupled. So, and of course, everything isn't central. So it's not that necessarily hard a thing to do, but I think it's a conscious decision. You say, all right, this is central to my system. I'm willing to be coupled here.
So I think it's interesting that the conversation has largely been talking about balances and trade-offs in systems, and understanding where your limiting factors are. It reminds me a bit of Cap Theorem and the idea that you can obviously only satisfy 2 of the 3 principles. What are your thoughts on that in regards to distributed systems and how that applies to what we've been talking about?
Well, so, I mean, obviously the Cap Theorem tells you that you will have to make trade-offs, right? There are, and to my knowledge, there are no examples of a system that, that violates that manages to make no trade-offs between the Cap principle properties. My favorite system design, in fact, it's come up before, is Spanner, and Spanner makes great promises in all 3 dimensions, but it doesn't violate Cap. It just hits the sweet spot. And the reason I'm bringing it up is because I think it's a great example of something that people should consider when they're designing and building a system. Is they acknowledge that they're going to have to make trade-offs, and then find the sweet spot for whatever it is they're designing that solves a wide swath of users' needs, and that does a great job of capturing the users' demands in each of the dimensions that they care about. But you should be aware that you're going to have to choose at most 2 of those, the Cap properties that you're going to truly solve. But I think a system that does a really good job in each of them, and not perfection. I mean, we were talking about outages earlier today, and outages happen regardless of what your system was designed for. You may have perfect guarantees around storage, eventual integrity, but that doesn't mean that your users are going to see perfection, because they're not. Their personal connection might be down to their internet provider. So, and what they really care about is their business and me. So I think that doing a good job of satisfying scaling needs in every dimension that you do identify, as we sort of talked about at the beginning of this talk, is more important than meeting a sort of a theoretical Cap properties test.
Okay. I think that, in the context of a messaging system, Paddy, I think I can see how those lines would get blurred, and deciding what that sweet spot is, because the latency of a message to be delivered is something that will be variable, and I expect certain use cases require certain latency guarantees. What are your thoughts, Paddy, on how that, I suppose, that thinking is applied at Ably?
How does it relate? So, so the first of all, sort of naively, the Cap theorem would have you believe that these are binary properties. So the system is either available or not available, and in reality that's never true. You get outages in a certain part of the world, but in a global system that you can't deny service just on the basis of a single regional fault. So availability and the other properties are not binary attributes. The other thing that Cap specifically applies to is understanding integrity of, if you want to build an ACID database, or you want linearizability as a property of your system. In our case, though, we get to choose the semantics. So we're able to say, in the specific case of messaging, in the case of a conflict between consistency and availability, then we get to choose exactly what semantics we decide are useful for our customers, and what things we guarantee to uphold in the presence of certain kinds of failure, and what things we don't guarantee to uphold. So we have a lot more flexibility designing our system than you would have if you were designing a relational database and you were trying to make the Cap trade-offs. So what we've done is, through a combination of what our customers tell us their requirement is, and our own understanding of what's achievable in practice.
What are your thoughts on fault tolerance, Paddy?
Fault tolerance. So I think you have to set out with the idea that everything will fail at some point. So you have to do things as a matter of routine so as to recover from certain failures. And then the decisions you face are, what kinds of failures am I going to handle routinely with no degradation of service, and what kinds of failures am I prepared to allow for some degradation of service. And in doing that, then you have to look at, well, how would I survive these failures? So what level of redundancy am I going to maintain? what is the cost of maintaining that, not just the resource cost, but also the performance cost, the operational cost of managing that redundancy. Also, if there's more than one failure, do I really think those failures are independent? So if I think that my failures are not going to be independent, so when one thing fails, then I have a greater likelihood of the thing I'm failing over to also failing, then no amount of redundancy is going to give me 100% fault tolerance. So it's a trade-off between understanding customer requirements, understanding the business operational cost of achieving it, and understanding the real-world engineering practicality of actually making it possible.
So I think I agree with Patty's comments about that. I think but another dimension of it to be really conscious of is to consider whether you should, how to balance between minimizing mean time between failures and mean time to recover. And, you know, in any system that I've worked on and in ones I know about, oftentimes this isn't done thoughtfully and consciously up front, but sometimes minimizing the time to recover works out much better than minimizing the time between failures. And engineers' natural tendency is to try to minimize time between failures, right? To make the system as reliable as they can. That's not always the right answer. And sometimes just making it recover really quickly from failures gets you where you need to go in terms of value to your customer and simplicity of the engineering. And you can, and it solves problems that you might not have considered. You know, I mean, by nature, trying to minimize mean time between failures means figuring out what's going to fail and preventing it from failing, right? Minimizing time to recover solves problems you never considered before. And we were talking about second order and unanticipated scaling problems. Well, this is sort of applying that same concept to the failure scenario where you try to minimize unanticipated failure problems too. And so this is something I was, hadn't considered, didn't learn until I went to Google. And at Google, they're super sophisticated engineers there. Obviously, this is one of the things that they taught me, is that stop at the beginning and say, okay, in every kind of area of failure, what are your areas of failure? That goes to what you just said. But then secondly, am I going to attack this area of failure by making the system recover very quickly from it, or by avoiding the problem through extensive tests and great design and so on? And I think there's a really important lesson here.
Do you think that applies also to dealing with unexpected load? I mean, there's an element of sort of hitting a high watermark, and that, I think it's that, from me anyway, my understanding is that the high watermark kind of sits almost in both camps, that you're saying, I'm willing to reject some work so that I can save the system and recover. But equally, I'm degrading the service at the same time, or degrading the service at least. I mean, how do you think that applies to what you've been talking about? I mean, is there anything specific you think our listeners would want to know about?
Well, I think just, reflecting what Paul said. So in terms of coping with load, so you've designed things to be elastic, they can scale when load scales, but then you have the second order problem, which is, well, how quickly can you do that? And you can do two things. One is you can operate with a margin of capacity to be able to handle a certain spike in load without having to scale, and then you can react to that instantly. Or you can build things to be able to scale very quickly. So building things to be not just inherently elastic, but inherently scalable, being able to react to spikes. You can reduce the complexity of the system potentially if your way to reacting to spikes is to be able to scale very quickly.
One area I think we haven't yet touched on is really the sort of people element of how you build and maintain a distributed system, and arguably this is the most important element. Paul, I think you've obviously got a huge amount of sort of experience and insight into this area. I don't know if you could share any of your sort of experience, wisdom on how to structure teams. Well,
I'm not sure that structuring them is the right question. I think that to build a scalable system, you need the whole team focused on that, right? So there's no substitute for just experience building these systems. You have to engage the team, and you have to make sure that people, that there's at least somebody on the team who has this experience, or you're not going to end up with a system that's scalable. But beyond that, I think that there's all sorts of, I don't want to call them tricks, but they certainly are, they feel like tricks, and they're effective at ending up with a design. Part of that is to make sure that the entire team, I'm just afraid here that I'm going to end up saying, what's the expression, mom and apple pie. I'm afraid that this part of the discussion is going to end up with a mom and apple pie kind of answer, because I don't think there are any silver bullets here. I think that it's important to involve the team in the design so they are all bought into it. I've made that mistake before a couple of times, where I had the idea in my head, the design in my head, and thought, that it was so clear to me, right? Bad answer. But there's other things you can do, like if there's a design question that is difficult and not clear, one of the things that I found really effective is to make, pick an advocate of, let's say, the two most likely solutions to the problem, and then have one person argue one side of that, and another person argue the other side of it, and then make them swap. And argue the opposite side of what they believe. And this has worked out great for me in terms of getting to a consensus, because it makes people look at the problem from the other person's perspective. And people don't want to argue the side of the question that they don't agree with or believe in, but it's really effective. The other thing about getting a team to build a system that scales both in the error space, which we were talking about a minute ago, and in the sort of production throughput space, which is where we started the discussion, is to have a conscious list of things that you're going to address and get those on the table early on. A lot of the things we've discussed today, if you gathered them into a little checklist, you can then make sure that you didn't forget to do. There's so many aspects of system design, right? And a lot of them are judgment calls. They're not answers. They're just, but if you don't consider those questions, you're not going to make good judgment calls, right? So having together a really coherent and inclusive list of the aspects of system design, really this is kind of a summary of what we've said today, is that having that checklist is what leads to, and then using the team concept to explore the checklist, assigning people to aspects of that checklist to consider and to come up with a recommendation and on a plan and so on. I think this sort of ties together the whole conversation we've had today, which is that there aren't silver bullets, but there are points that need to be addressed, consciously and thoughtfully, and that if you do so, you end up with both the good teamwork side of this whole problem addressed, and with good answers to the technical questions that need to be addressed. So.
It's interesting. One thing that I think is also probably quite important to consider is complexity of the system. And I'm interested to know how often you've had to reduce complexity of a system, knowing that it will affect the ability for it to scale potentially, because the complexity is too great for the team to maintain. And so as an example, of course, would be Rob Pike famously talking about how Go was designed to not necessarily be the most feature, a language with the most features, but a language that allowed the team to work coherently together and understand each other's code. Has that ever happened in the sort of the designing and building of distributed systems?
Yeah, so it's a great question. Partly because it's what I would consider my largest failing as an engineer. The place where I get into most trouble is not simplifying when I should have. So as a lesson to my future system designs, and as a lesson to other people maybe who are a little bit like me in this way, I think it's a brilliant thing to point out, is that that's a choice that you should lean towards. Especially if you're inclined like me to design things that are maybe a little too complicated. Intentionally restricting both the capabilities, but at the same time the complexity of your system, I think is a brilliant way to end up with a system that works well. And it's like going a little bit too far and then coming back to your comfort zone. Is it just you end up with a system that is works better and is inherently more understandable. And those are both important points.
Yeah, definitely. Less is more a lot of the time. I think you have to remember that fundamentally building software and systems is a human activity, and it's performed by humans, and maintainability is just as important a property of the software you write as reliability and security and performance and all those other things. And ultimately, you do have to make sure that you build things, within the cognitive limits of the team that you have.
Yeah, and in fact, that's as a leader of one of these teams building something, something that I wish I had done before would be to stop and say, okay, here's the team. My team has to build this piece of software, right? In a practical, I want something to come up that's out of this effort that's beautiful and works really well. I have to take into account the just general capabilities, the expertise level, the experiences that they've had in the past, and even how well they work together, to use that to influence what you just said about choosing what level of complexity I'm going to design the system to.
I think it would be really nice is to extend a sort of set of recommendations to our listeners to just say, if you're going to, after watching this video, what actionable things can you do to sort of take this learning and apply it to distributed systems that you may be trying to build? Paul?
Well, so I think that I mentioned earlier about having a checklist, okay? What I don't believe in is that there is one checklist that's right for everybody. That I should put down my checklist and put it on the website, and then you guys can use it. I think that each of the engineers watching this video is facing a set of problems with a different team in a different environment, and has his or her own personal sort of experience level and needs. So I'm hoping that maybe on review, or maybe you've been doing it as you went along, you've heard some things that resonated with you. And so my final point is only that you should consciously make that effective by turning it into a list that you can use to remind you not to omit things when you're doing your next system design. Because the design of a system is, in my opinion, it's the most complex thing undertaken by mankind, is the design of a large software system. How many man years of efforts go into it? And it's not just man years of work, it's man years of thought, okay? It's unbelievable, right? So there's no way anybody I know can keep this whole thing in their head without external aids. I advise that you create external aids customized to yourself and to your problem and your environment, and then use those, apply them to the systems you're designing in the future.
Yeah, all I'd add to that is to go back to what we said at the very beginning, which is a computer science textbook will list out the problems that you have to face when you're building a distributed system. You have to cope with unreliable networks, you have to cope with latency, you have to cope with consistency issues. But really what we've been talking about here is what you learn when you go beyond that, when you design things to operate at scale, and when you have experience of operating them. So what I would encourage people to do is get away from the textbook and just go build stuff. And that's the best way to find out how to do this for real.
Well, thank you, Paul and Paddy, for being here today. And that's it for our first episode of Distributed Deep Dive.